Hello, everyone. Anyone here? And I believe I'm recording. Mhm. Good morning, Denise. Are you there?
Yes, sir, I'm here.
Good morning. How are you?
Morning, I'm good, sir. How are you?
Good, thank you. Good morning, Brian. Good morning, Brian, if you can hear me. Okay, well, let's
Good
begin.
morning.
Oh, good morning. How are you?
Doing good. And how about yourself?
Good, thank you. Happy Monday.
Happy Monday.
And I don't know what happened to Jocelyn. Okay, well, let us begin, and we start a new chapter, and it's a different chapter. It analyzes some different topics, but it uses the concepts we were just studying. And good morning to you, Jocelyn. Okay,
Good morning, sir.
how are you? Okay, so let's,
Good. Thank
good.
you.
You're welcome. Okay, so I'm gonna go right to WebAssign, and the first section is an introduction. And I think I'll use this to also talk about what's coming, but most of these problems were problems you would have practiced in, well, part of them are problems you would have practiced in the second semester of pre-calculus. There was just like 2 sections on sequences, and then we extend it from there. So I want to start with, well, I guess we could start with this one, number 4. And for some of these problems, I won't need to do any work on the notebook as it is an introductory section. Okay, so everyone, let's start. And can you all see the WebAssign page?
Mm-hmm.
Okay, so here we have a given formula. And notice it doesn't say f of x equals all of that. It is this term or this notation. So it's not this formula. And so that's the first thing we have to understand, is that this is a function and the domain would be all x values. All real x values would be the domain. Whereas when we see a sub n or b sub n or c sub n, just like someone decided to start with f of x, and I guess because function starts with the letter f, maybe, I don't know. This tells us it's a function, and well, this would be all real numbers except 0, but because when you put 0 in, you would be undefined and you'd have a vertical asymptote. But this would be a graph of all of this, and this is a graph when the domain is the set of positive integers only. So it's positive integers, and sometimes they'll tell you, sometimes they'll tell us to include 0, but they'll tell us. So so most of the time it will be positive integers only. And good morning, Joshua. So the domain, when you see this, it's just positive integers only for n, unless they tell us including 0. So here, everyone, when we start to graph points, where it's going to be starting at n equals 1, and you notice these graphs, there is no graph at n equals 0, and then sometimes there will be. On this one, it wouldn't be defined anyway, so there couldn't be a point. But there will never be any graphs with domain using these domain values that are negative. And so that'll never happen. And it normally will start at 1, or you could even say, oh, let's start at 4 instead. But for now, they'll start either with 1, or at minimum, it could start at 0. And that's why you see only points instead of a curve. So we're not going to see something like a continuous curve that would have an infinite, that would have all these complete points all connected. We might still have an infinite amount of points. It's just that they're an infinite amount of individual points, okay, that are given by some rule or some formula. So that's one. And now, again, A sub n is supposed to give us a clue that this is just a list of numbers, not a complete graph with a completely connected or continuous amount of points. Okay, so for the entry question here as an introduction question, it's just merely, okay, let's make a little table. Oops, I get used to writing X. So there's a couple ways you could write this. We could still say n, and so instead of X and Y, you would say n and then A sub n. And that's instead of saying X comma Y like we're used to. But in here, you know, depending on the function, the domain can be most real numbers. There might be some exceptions, but that's the domain issue. Here, we have to start at minimum, it could be 0, but they will have to tell us. Otherwise, you start at 1, 2, 3, 4, unless they say, hey, only, if they say something like this, comma, n greater or equal to 4, for example, well, that means you don't start until right here. But otherwise, if they don't say anything, then that means start at 1. So we're going to not start at 0 because they didn't tell us. And then if they don't tell us anything, which they did not tell us anything, then that means start at 1. Okay, so to now, we just want to get the mappings now. And again, this is going to be a collection of points. A sequence we typically think of, it's a list, or it's a collection of objects or a collection of numbers, they're objects as well, that have some kind of order that whoever decides how to order them. So you might order a collection of books by the alphabetical order of authors, or maybe oldest to newest. Who knows? It would be that person's choice. But here, a sequence has a mathematical formula, and we simply are going to fill in the first few terms, and then we're going to match it with the graph. And again, notice the graph are just points. So, okay, any questions so far?
No.
Okay, good. So here we go. So for example, Jocelyn, can you, oh, and then there's this part right here. We need to get used to this little expression here, this -1 to the nth power. It's not a big deal. And if you notice, if we start putting the 1, the 2, the 3, that has an impact on of course, all of this has an impact on what the values are, the output or the range values. So when we put 1 in here firstly, so we're going to get -1 to the first power. And so here we're going to get a sub n equals, I won't write all this out all the time, but -1 to the first power. Oh, that was the same color. Okay, to the first power, because that's the n value over n, which is 1. And now we just compute. So -1 to the first power is -1 divided by 1, and that's -1. So we have that. And so forth. So we want to match this graph, but so the first term is at domain value n. Notice there's an n instead of an x. And this is not a y-axis, but the a sub n axis, which is our range axis, our domain axis. Okay, so the first term has to be at n equals 1, which is right here, and the mapping is -1. Well, that is a -1. So that means this could be the graph. We could eliminate, if possible. This was at n equals 1, and the mapping is up here at 5. Well, then this one's already out. And this one at 1 is -1, so that's possible. So we can't cross that one out. But here at n equals 1, we get 5 again, so this one's out as well. So that means it's either this one or this one. And now we just plug in continue. So if we put a 2 in, so right here we would get -1 squared divided by n, which is a 2. So for this one, we would get a sub n. Well, and really you could say a sub 2, because now you're replacing n with the 2. But so technically we would want to write here a sub 2. So a sub 2 is when you put an n in, n equals 2 for the n, and now we have -1 squared and then divided by 2. And of course, -1 times -1 is +1 over 2. And so that's this next term. And then let's quickly fill in the rest. So -1 to when n equals 3. So we'll have -1 cubed divided by 3. So Jocelyn, of course, what's that going to be? -1 cubed would still be
-1.
And then divided by
3.
3. So that'll just be what? -1/3?
-1/3.
And what about when n is 4, Jocelyn? What's -1 raised to the 4th power?
1 over 4.
1 over 4. Good. So notice these terms are alternating from negative to positive to negative to positive. And that's because of this -1 to the nth power. So we'll see that a lot throughout the chapter. And that's like a giveaway to tell us, oh, this makes these terms potentially alternating. In most cases, alternate. There are some other strange possibilities, but by and large, it's when they alternate. And depending on this exponent could be an n like it is right now, an n plus 1, an n minus 1. There's an infinite amount of possibilities for this expression up here. But when you have -1 with some kind of n expression, then that usually means it's going to alternate. And in this case, it starts out with negative, positive, alternating like that. So this we call an alternating sequence because it's alternating from negative to positive to negative to positive. So this one's alternating, but so is this one. Negative, positive, negative, positive, negative, positive, like that. So another way to, well, before I say this other part, let's just finish matching. So of course, this one was correct. So at the first term, but the second term, a sub 2, is equal to 1/2. And clearly right here at n equals 2 is not mapping, it's mapping to 1 unit up, not 1/2, which would be like right here or something. So that means this one's out. So by default, it better be this one. And if we check at 2, 0.5 is certainly believable, and so forth. The third term is negative 1/3. So at n equals 3, negative, this down here is certainly believable to be negative 1/3, and so forth. Okay, so this is the correct one right here, and we would fill that in, of course, to complete the problem. Any questions so far?
No.
No.
Okay, good. And now I just want to show you a couple of other things here. One is just notation. Another way to write out the terms other than in a table form is just to write like this. So when n equals 1 and n equals 2 and so forth, and dot, 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 ellipsis, and then we could write somewhere else above it or below it, we could write a sub 1, a sub 2, and so forth. And then just, and it's our choice. You could write them right here, equals, you could put it underneath. It's kind of typical or common to write it like, not put equals here, but just to write the numbers. So negative 1 and 1/2 and so forth. So no big deal right there. And see, as we go out, then we'll keep getting more terms. They'll alternate negative, negative, positive forever. So that's because of this negative 1 to the nth power again. And as we go out, what we want to examine is a couple of things. So this problem is done, but very quickly, the section is going to change into asking us some more things. And this is what brings us back, excuse me, to the last couple sections in chapter 8. So one of the things we'll be looking at here is what's happening to these individual terms of the sequence as you go out forever. And as soon as we say go out forever, that should remind us of a word, a mathematical word we've been using a lot. Yeah, it starts with an L. So can you guys help me out here? What does that bring to our mind?
Limit.
Limit, good. So we're going to be asked either in notation or in prose or just verbally, hey, what's going on with these terms as you go out forever? Which is a limiting question. And remember from chapter 8, when we take a limit, we want to be able to determine its limit. So we had this determinate form of a limit versus an indeterminate form. And when we were at an indeterminate form, that just meant it's either, and we categorized it as friendly and unfriendly. And that just meant when we analyze the limit by directly substituting, excuse me, we were not able to get a determinate value yet, and that's when we got infinity over infinity or 0 over 0. And then we could use L'Hopital's rule. And if we had an unfriendly indeterminate, we had to use some kind of manipulation to change it into a friendly indeterminate form. And then remember, once we are able to determine the limit, well, then the limit is determinable. So our goal is to figure out what is the determinant value. So that's what brings us, this whole chapter is going to be about this kind of idea in two ways. One is just what is going on with these terms as we go out forever. What is the determinant limiting value? And remember, there's 4 possibilities. Well, yeah, 4. One of them is not that popular, but 4. So one is, well, maybe you guys can help me out here. So what were the determinate limiting values? What were the possibilities? One of them was when we take the limit and we get what?
A finite numerical value.
Good, that's one. And what's another one? What's a second and a third?
The negative and positive infinity.
Excellent. And then there was a fourth, which it happens, but not as often. What was the last one?
Negative infinity over infinity.
Well, good. That would be when we get a friendly indeterminate, and then we would have to use L'Hopital's to change the form of the equation so that we can make it into one of these determinate limiting values. So that's when we get indeterminate.
When it does not exist.
So not exist, good as when. Not exist is 3 of those 4 possibilities, and one is infinity, one is negative infinity by itself, and the fourth one was when the graph when it goes up and down like this forever and it just keeps oscillating, and so it never settles down. So the other fourth type was when it oscillates, or we could even say alternates, or oscillating. Okay, so what we want to be able to do here what we want to be able to do is to, this question's done, but I'm using it to ask about what's most of the section's about, and that is, what are these terms going to do? They are alternating. Remember, it's not going to be a curve, though. It's going to be a bunch of points. What would be the, if we kept going here, what would be the next term? This was negative, positive, negative, positive. What would be the next term, of course? That would be when n equals 5. and what would happen, so what would be the next term right here? So the 5th term of the sequence. If you put a 5 here, it's going to, -1 to the 5th power will become -1, and on the bottom we'll just get what? -1 over what?
5.
5, good.
5.
And I think that was Joshua. What would be the next one, Joshua? Would it be negative still or positive now?
Positive.
And 1 over what?
6.
Good. And the next one?
-1 over 7.
Mm-hmm. And this continues forever. So, Josh, what do you think's happening to these fractions? In the top, we're either going to get positive or negative, but these overall, 1 over 6, 1 over 7, 1 over 8, 1 over 9, 1 over 10. Yes, they're alternating between positive and negative, but what are these numbers? If we put these in our calculator, what kind of numbers, aside from saying positive or negative, what kind of, are they getting closer and closer to something? Or that means either infinity. That would mean these numbers are getting bigger and bigger and bigger positively only, or they're getting bigger and bigger negatively only, which would be negative infinity, or they're oscillating, which means alternating. There's actually a slight, you can alternate, we can alternate. So alternating doesn't necessarily mean positives and negatives all the time. It could. So it could mean positive, negative, positive, negative, positive, negative. But it also could mean oscillating or alternate. It could also mean this. Say this is like a 4. Say this is like a 2. Say you get 4 on one term, the next term's 2, the next term's 4, the next term is 2. This is also oscillating, or we can say alternating, but it doesn't, they're not alternating between positive and negatives. This is another type. We could also have them alternating underneath where they're always negative. So anyway, so these are alternating, but what? Are these numbers getting bigger and bigger, like closer to infinity, or only, or they can't be because they're alternating, positive, negative, positive. So there's no way these terms are getting closer and closer to infinity only for 2 reasons. One, these numbers are getting smaller, not bigger. And secondly, they're alternating between negative and positive. So there's no way that these can go towards infinity only. And there's no way these can go negative to negative infinity only. Because these numbers are not getting, these fraction values are not getting, when you divide them in your calculator, they're getting smaller and smaller. So these are not possible. Alternating, that's another type of a determinant where the limit does not exist. And these are alternating, but it would have to be these, any of these kind up here, where they're alternating. This is alternating positive, negative, but they're not getting closer to anything. They're just staying up here and staying down here, and they're not merging towards any common number. And the same with this kind. This is alternating, but they're just alternating between 2 and 4, 2 and 4 forever. So this is also not going to be converging or have a determinate limiting value. So this would be the type where you would say not indeterminate. It's a determinate, the limit is the determinate value and it's infinity, or it's negative infinity. But in this case, this would be the alternating, or we could say oscillating. But when you have just dots, it's more common to say alternating versus, this is what we mean more when we say oscillating, because it's continual, it's a continuous graph here. So you'll start to hear the word alternating more than oscillating. Okay, so so we're getting there. And so the 3 types of, there's 4 types of determinate limiting values. And that's a finite, I'm not gonna write them all down again, but a finite numerical value, infinity only, negative infinity only, or alternating, but not alternating towards any finite number. They're not getting closer and closer to anything. Here, this graph is an example of alternating negative, positive, negative, positive. But they are getting closer, even though they're alternating. It's not like this kind where they're just going up and down from 2 to 4 forever. These are not getting closer to any number. And neither is this one. This is positive, this is negative, positive, negative. They're not getting closer to anything. But these are alternating, and they're alternating with respect to their positiveness and negativeness. But they are getting closer and closer to the same idea you saw over here, and we just didn't say it yet. And Joshua, what did we come up with an idea? We didn't say it, but What do you think these numbers are getting closer and closer to? It is a finite value. And what finite numerical value would that be?
0.
Very good. 0. Yeah, we're getting closer and closer to 0, but in an alternating fashion. Yeah, and it is, so this is a determinant value. It's a finite number. And even though it came from an alternating sequence, it's an alternating sequence, not like this type, not like this type. The only other type is, well, actually, there's more than one other type. You could alternate like this. No, that's not true. Sorry, what was I thinking? No. So the only other possibility was like this. This is not here. They're alternating, but they're always negative, and they're not getting closer to anything. Okay, this might be whatever, -1, and this might be -4. But they are alternating between -1 and -4, but they're not getting closer to anything. So this would be a determinant, but we would say it does not exist because of the alternation or the alternating the alternating of these terms or these dots or these points. And these are alternating, they're just always positive, and they're not getting closer to anything either. So this would be an undefined or does not exist limit, or we would say this limit of this sequence diverges, and it's the type of this alternating type of divergence again. Okay, this is alternating, but because they're getting closer and closer to the same finite number, then we do have a limiting value. It's a finite numerical value. So if we're going to be asked in this assignment in the next many sections, what is the limit as n approaches infinity of this expression right here, which represents a sequence, a list of numbers, and then we would say the limit is 0. Or we would write the number 0, and then we would say what class does this limit then does it exist? If we get a finite numerical answer for a limit, that means the limit what does not exist or exist?
Exists.
It
Exists.
exists.
Good. Another way of saying the limit exists. The limit what? Converges, diverges, what?
Converges.
Converges. It converges to 0, huh? The only time we use converges is when it's this type of determinant limiting value, the finite numerical. If it's determinant the other 3, which is infinity only, negative infinity only, or alternating, but alternating and never getting closer to any single finite number, then we say the limit does not exist, or we say the limit diverges, and then or we say this sequence, which is this list of numbers, diverges. But in this case, the limit of this sequence does get closer and closer to a finite numerical, a single finite numerical value, which is 0. Okay, so any questions there? We spent a lot of time on this one problem, but I was using it to talk about the ideas here. So, any questions here?
No.
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 Okay, let's move on. So there's, I guess I need to erase all this scribble, and yeah. So I guess we could check the answer, and this was number 4, and it was this one. And we're good. And there's some other ones right here, and I'll let you guys do this one. You can write them out. By the way, we can also go faster here, but I'm gonna wait. I'm gonna wait for another problem. So let's see. This one, they're not asking us to match a graph, just what are the first 5 terms. So you're just gonna put in a 1 and for n, and then a 2, and then a 3. And this also, so let's look at this one. And so this one here, we want, well, it has it right here, the first 5 terms. So we just plug in the 1. So we're gonna get sine of 1 times pi over 2 is pi over 2. And the next one is gonna be sine of, so when we put a 2 right here, the 2 times pi divided by 2, the 2's cancel out, divide out, and we're just left with, what are we left with there, Denise? We're just left with what?
Pi.
Pi. And we continue. A sub 3 would be sine of, Joshua, what's going to be this one if we put a 3 up there for n?
Sine pi over 3.
3 pi over, I'm not sure if I heard you correctly, but you put a 3 right here, 3 pi over 2, is that okay?
Yes.
Okay. And the next one, Brian?
It'll be sine 4 pi over 2.
And what's that going to reduce down to?
It'll be 2 pi.
Mhm. And the last one, Denise, will be sine of
5 pi over 2.
But realize this is a sequence that would go on forever and ever. We could keep going here, but they just want us to fill in the first few terms. But I want us to keep in mind the more important topic here, which is not just writing down the actual terms of the sequence, but what are the terms of this sequence doing as you go on forever and ever? What kind of determinant value is it? Is it the converging type, which is getting closer and closer to a single finite number? Or is it the other, one of the other 3 types of determinant value, which is when it diverges, or we say the limit does not exist, which is infinity only, negative infinity only, or an alternating type where the alternation of all the sequenced, the range values, all these points are not getting closer and closer, but they're just alternating and not getting closer. So let's see. Okay, well, you could put those numbers in a calculator and get the sine values, but these are, this is pi over 2, and this is pi, this is 3 pi over 2, and 2 pi, and so forth. So we can also use the definition of sine, which is the definition of sine is y over r. And if we use radius 1, you could pick any radius you want except for 0. You wouldn't have a circle then. But anyway, if the radius is 1, that's just the simplest circle. Then from here out to here would be 1. And so that's why this point would be 1, 0. And this point would be 0, 1, and so forth. And this point here would be at pi radians. This is pi. This is pi over 2. This is 3 pi over 2. So in other words, every 90 degrees, you go another pi halves. So 1 pi halves, 2 pi halves, 3 pi halves, 4 pi halves, 5 pi halves, like that. And x comma y And the same thing here. 0, -1. So let's see. So Denise, can you help us here? What's going to be for the first term, which is 1 pi halves, which is up here on the top. So the y value divided by r is always 1, no matter where we're at on the circle, the radius is 1. So what's going to be the y over r value here?
1.
1 over 1, 1. So we're going to put here 1. And that means up here we have a 1. So there's the first term of the sequence, or the first range value of the sequence. And the first domain value was 1, n equals 1. The range value was a sub n, or we say in this particular case, a sub 1 equals the 1. Okay, the next one, Denise, that would be a sub 2, and that's when we plug the 2 in and we got sine of pi. Here's pi, but what's the y value this time?
0.
So 0 divided by radius 1 is going to be what?
0.
0. So it comes down here. And the next term is 3 pi over 2. So Denise, what's that going to be? Y over r here would be what?
-1 over 1.
Which is?
-1.
So that's right here. And we may remember, class, that the sine graph, if we drew all the points, it's this continuous graph that oscillates from 1 to -1 forever. Yeah. So that also kind of gives us a clue what, well, that's what's going to tell us if this sequence is going to converge. The determinant limiting value, is it a converging determinant value, or is it a divergent determinant value? And if it is divergent, which one of the 3 types of divergent is it? Infinity only, negative infinity only, or alternating, or we could say oscillating. But again, we don't use oscillating so much when we don't have the entire curve, but just the individual terms of the sequence versus the entire function. Anyway, so, and what about at 4 then, Denise? The a sub 4 was 2 pi. Here's 2 pi radians. And what's the y value here?
0.
So 0 over
1.
which will be
0.
0. Good. And that's right here. And the last one, Denise, what's sine of 5 pi over 2 going to be? That's right up here. And that's going to be what?
1.
So as we keep going around, we're just going to keep getting, this is going to repeat. So first of all, the question number 2 is simply to write down these answers here. 1, 0, -1, 0, 1. The more important question is going to be this, which they didn't ask yet, but I'm trying to teach it to you now together. So as n approaches infinity, oh gosh, of this, by the way, we can also write just a sub n, which is the same thing as saying the limit as n approaches infinity of the sine of n pi over 2. So this and this is just shorter to write it. So what kind of determinant value is this limit? Or what kind of determinant value is this limit of this sequence have? So if it's a finite, single finite number, well then that's the convergent or the limit exists type. Or if the other 3 is, I keep repeating myself, infinity only, negative infinity only, or the alternating type, but not towards any single number. So Denise, what do we have here? Is it converging towards any single finite number?
I don't
This,
think so.
no, because what's going to happen after this? Yeah, what's 6 going to be? So it went 1, 0, -1, 0, 1. What's the next one going to be?
0,
And the next one?
-1,
And the next one?
0.
And it's going to do this forever.
Mm-hmm.
So, yeah. So then are all these terms of this sequence or these dots, are they getting closer to any single finite number, or are they just, or not?
No.
No. So that means it's not a finite single number, which means this limit exists or does not exist?
Does not.
Does not exist. What's another way of saying the limit does not exist? The limit what?
Diverges.
Diverges. Good. And what's more specific than just saying diverges or does not exist? What's the explanation of when we say it diverges? Which one of the 3 possibilities is it? It's because of what?
The oscillating.
Or what do they like to use more when they're just terms of a sequence? Is
Alternating.
Alternating. It's the alternating type. And the alternating type where they're not getting closer and closer to any finite number. So that's what we would put right here. Diverges, we would say here. Okay, and if they ask for more explanation, then we would say because of this alternating type. Any questions here, class?
No.
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 Okay, very good. And if we go back and we can type these in and hopefully we are correct. And okay. And we're good. Okay, and by the way, this right here, number 1, it has a -1 multiplied by 3/4. So what's that -1? This could be also written like this, everyone. You could factor this -1 out, and it would be -1. So it's kind of important we get used to that. It's really could be thought of as this as well. You don't have to separate it. But if it is separated, it should be a very loud slap in the face, if you will, or bright light that says, this does what to the terms of the sequence? This -1 to the nth power. That's an n right there, up here. Brian, what does this -1 to the nth power do to the terms of the sequence?
I would say it's kind of like problem number 4 where it alternates.
Very good. And does it alternate like from just like a positive number to another positive number, or from a negative number to another negative number, or is it alternating from positive and negativeness?
From positive to negative.
And it could be, the first term could be positive and then it alternates, or the first term could be negative and then it alternates, yeah? So now when this alternates, then positive and negative, Brian, what kind would this be? I'm just gonna make it up, but what if we had this? Alternate, and let's just say this is a 1, or let's say this is 2 and this is -1, just pretend. Alternate, 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 alternate forever, yeah? So this is alternating type. But is this, what kind of alternating type is this? Is it a diverging alternating type? Is it a converging alternating type? And you're like, wait a minute, what is alternating converging type? Well, the only type that can alternate and converge is they both, by the way, have to be one, it has to be the positive and negative type. It can't be alternating like above and, like this on the positive side only, or it can't be like on the negative side. Well, I didn't draw these right, sorry. But anyway, it has to be, one's positive, one's negative, and they're getting closer and closer to the same finite number, to a single finite number only. Is this that I have drawn right here, Brian? Is this certainly is alternating, yeah? But is it getting, are these dots right here getting closer and closer to any single number?
No.
No. They're just going from 2 to what?
-1.
So this would be alternating type, but determinant alternating type, but to a single finite number, or just alternating?
Just alternating.
So this would be what kind of example right here? It's determinant, it's alternating, but what? The converging type to a single finite number, or a diverging type?
Diverging.
Good, that would be this picture. I'm not saying that's what happens here, but that's what this picture would be. Are there any questions from anyone else about that idea?
No.
No.
Okay, so let's see what kind of alternating type is this one actually. It's not this. So we find out by, well, getting the points. So, okay, so we put in, you can leave it like this or just leave it the way it was, either way. So let's see. If we leave it like this, then, well, let's just fill these in. We can start to go a little faster here. So what's going to happen, Jocelyn, when we put a 1 right here for the first term? They're telling us, remember, they're going to tell us, well, here they're telling us start at 1. If they don't say anything, then that means start at 1. If they give you something else, start at 0, or they could say start at 2 or 3 or 4. But anyway, so so let's find out. We already know it's going to be alternating because of this, which is really hidden in here. So the question is, what kind of alternating? So, and you probably have already figured it out by now, if you were thinking ahead a little bit. So Jocelyn, what's this going to be here? -3/4 to the first power will just be what?
-3/4.
Mm-hmm. So that's, let's just pretend that's -1. Up here is +1. So -3/4, no, it's somewhere here. So let's say it's like right here. Okay, and then what's the second term going to be, Jocelyn? -3/4 squared. What's the negative times the negative going to be?
Positive, it'll be 9/16.
Good. And 9/16 is kind of a little bit bigger than 0.5. So it's going to be like right up here. And now the third term, Jocelyn, what's the third term going to be? -3/4 cubed. So is that going to be negative, positive? What's that going to be?
Negative.
Good. So that's the alternating part. And then what's 3 cubed?
It's gonna be 27/64.
Mm-hmm. Now, if we had to, we could go into a calculator and start plugging these numbers in and to see. But 32/64 would be half. If it was 32, half of 64 is 32, but it's smaller than 32. So this is not even -0.5. This was 0.5, and now it's negative, but it's even smaller than 0.5. So this is what starts to give it away. This was negative, down negative 3/4 or 0.75. This was up 0.5, and this is down even less than 0.5. So, and then the next one. So I hope you're already thinking ahead and you're saying, yeah, these are alternating, but are they getting closer to some finite number or not? And Jocelyn, what about the next one then?
It is 81 over 256.
Good. And it sounds like you have a calculator there. What does that divide out to about?
Let me see.
Do you have a calculator, Jocelyn?
It'll be 0.316.
And what was this one right above it? 27, negative 27 over 64. What was that?
Negative 0.4218.
Thank you. Oh, that's supposed to be an 8. Okay. So 0.316 is even, it's positive, but it's even closer yet to the x-axis. And the last one, Jocelyn, when you put a 5, negative 3/4 to the 5th power, and that's going to be negative. So 3
Negative 243.
to what? 243?
243 over 1024.
Thank you. And what happens when we divide that on our calculator? It's going to be negative, but it better be smaller
Yes,
than
negative 0.237.
Okay, good. So now it's negative, but it's even, this was 0.316 above, and this is negative 0.2, so it's getting closer. So I hope you all can, again, I'm trying to prepare you for the rest of the lesson and the rest of the chapter, instead of just only talking about this, because I don't think that that's as beneficial for you all. So we can fill in these numbers easily enough, but more importantly, then Jocelyn, what do you feel would be what's going on with the terms of this sequence as we go out forever? Is it what kind of determinant value is it?
Approaching 0.
Approaching 0. Very good. So, and that's a single finite number, isn't it? Yeah.
Yes.
So that means it is getting closer to 0. Well, first of all, any questions on that? Why the reason that it's getting closer and closer to 0?
No.
Okay. And now, so what do we say then, Jocelyn? The limit of this sequence is getting closer and closer to 0. That is determinant. It's a single finite value. It's that type of determinant. And therefore what? This sequence, or we say this limit, what? Converges, diverges, what? Jocelyn?
Yes.
So what do we say about this limit here, since it does approach a single finite number, which is 0? Therefore, we say this limit or this sequence, what? Converges, diverges, what?
It converges.
Converges, good. Towards what?
0.
To 0, good. It converges to or towards 0. Mhm. And that means what then, Jocelyn? This limit, does it exist? It does not exist? What else could we say?
It does exist.
It does exist. Okay, good. So I keep repeating all those things because I've just known over time in a history of teaching this kind of stuff that those ideas can get people really lost because the people explaining it use them differently, or sometimes they'll say it one way and another way, and it can confuse people. So I hope that makes sense. Any questions here?
No.
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 Okay, so you could put those terms in easily enough and check it. Let's go on. And okay, so aside from this little exercise, the remaining problems are doing exactly what we were practicing extra, which was to analyze the limit of the sequence as it goes out forever. Or in other words, we just say analyzing the sequence. We can just say that, and that means the same thing. What's happening to the terms of the sequence that is given to us? So, for example, then that's what all these are about right here. So, for example, let's just look at a couple here. Oh, I don't know. How about number 10? So number 10, here's the sequence. They could ask us to write down the first 5 terms. We could even graph them, and that would give us maybe more comfort in knowing whether it does, what kind of determinant value it does have, the converging type or one of the 3 diverging type. But we can also do it without looking at the graph and writing a bunch of terms down by just taking the limit. So literally taking the limit. So what we can do here is take the limit. So I hope we all understand that. We could graph it like we were just doing, or we could just bypass all that and take the limit and see, do we get a single finite number, which is a converging type, or is it one of the 3 diverging types? Okay, and this is where our practice of limits in the end of the last chapter, it helps us out, yeah? So, okay. So what happens when we take the limit? So if we put infinity down here, of course, Denise, the 4 times infinity is still what?
Infinity.
And infinity to the 5th power is still
Infinity.
And when you put on the natural log graph, remember, look something like this. So as you go out forever on the ln graph, this graph goes up, up, up slowly forever. So what's the limit as n approaches infinity of ln of infinity? It's also what?
Infinity.
Mm-hmm. So what did we get here, Denise? Did we get a determinate limiting value yet, or is it indeterminate?
It's indeterminate.
And according to your crazy teacher, what adjective did we, so this is indeterminate, and what kind of extra adjective did we add on to that?
Friendly.
Friendly, but I hope that helps everyone. So then when it's a friendly indeterminate, of course, so what can we do then, Denise, to try to make this limit into determinate form, which means then we're done. Analyze.
You're gonna find the derivative independently of the numerator and the denominator. Question, how do you know n is approaching infinity? Where did it say that?
Good question. It didn't say anything, did it?
Yeah.
So, but it does say this. Can you read this part up here?
Determine the convergence or divergence of the sequence with the given nth term. If the sequence converges, find its limit. If the quantity diverges, enter diverges.
And I wish they would have been more specific than just this, because this means it could be one of these three: infinity only, negative infinity only, or alternating, but not alternating to a single finite number. Okay, so it would be nice if they would to ask us, so then we could keep being reminded that diverges means one of these three. Yeah, and converges means a single finite number. A single finite number. So you're right. I don't see anywhere there they say take the limit as n approaches infinity. But by this point, we're supposed to be able to have the somewhat mathematical sophistication to say, okay, when they're asking us the convergence or divergence of a sequence, that in itself means what's happening to all the terms of the sequence as you go out forever. Does that make sense?
Is that for every question?
For every question, if they ask you to determine the convergence or divergence of a sequence, then that's what it means.
So, okay, every question that's exactly like that, n is going to be approaching infinity.
Yeah, not only exactly those words, but if just the general idea is that they say to us, finding the convergence or divergence of a sequence, yeah?
Okay, so we're just assuming n is approaching infinity.
Yeah, so we're not even, yes, that's correct.
Okay.
Is that part okay then?
Yes.
Okay. Now, so you said, Denise, take the derivative independently. Well, what could we do if we wanted to? Because n represents a positive integer. If we wanted to, we could use a property of ln and bring down what? If we wanted to. That's not even differentiating yet.
You can bring down the 5.
And you're like, why bother doing that? Well, you don't have to, but it just makes the derivative a slightly quicker is all. So, or you could have left it like that and you still would have gotten, we still would have gotten there anyway. So I'm just going to suggest for us to just move that 5 down first. Any questions with that?
No.
The graph of ln of n to the 5th and 5ln is the same graph, okay? So, yeah, I never really said it that way before. It kind of startled me. I have to think about that. But anyway, I know you probably can't read that. That's 5ln of n. Oof. And now we're going to take the limit as n approaches infinity. On the rest of the sections, I'm gonna write it on my notebook. But so what is the derivative then? Oh, another thing is technically, if you use L'Hopital's rule and you take the derivative, to take a derivative, you have to have a continuous function. So technically, if we so if you read in the book or something, they would be writing it as x instead of an n. And so to be technical, you cannot differentiate a function if it's just a bunch of dots. If the function just represents a bunch of dots, well, then it's not differentiable. But so technically, if you put the variable x, then you are stating that it's a continuous function, and now you can differentiate it. So right here, I would just not put this part yet. Okay, so now, so that's what we'll do when we have to use L'Hopital's rule. So what's the derivative of 4x then, Denise, with respect to x?
4.
And the multiplied 5 is waiting. And what's the derivative of ln of x?
1 over x times 1.
Very good. I like that. You said times 1. That's excellent. And now simplify this. Depends how you want to write it, but we can have 5 over 4 times 1 over x. And now go back to ends. There's also a theorem says you could take the limit right here with the x's, and whatever you get, it's the same thing with the ends. So either way. So, oops, that's supposed to be an n. And now what, Denise? 1 over a larger and larger number gets closer and closer to what?
Infinity.
So you're right, infinity will be the number on the bottom.
Mhm.
So as this number on the bottom gets larger and larger, closer and closer to infinity, what's 1 divided by a larger and larger number? Get closer
0.
to 0. And what's 0 times 5/4?
0.
0. So there is our limit. We now know what happens if we did graph these terms, this sequence, and we went out forever. It would get closer and closer to a single finite number. And so that's this kind. So then what do we say about this, Denise? Is this sequence then, we've now found the determinant value, the determining value of the limit, or the nature of the terms of the sequence, and we got a single finite number. So what does that say then about the sequence? Is it diverging or converging?
It converges to 0.
Converges to 0. And what does that say about this limit? Does it not exist or exist?
It exists.
Yeah, the limit exists. Any questions here, class?
No.
No.
Okay, so here, it does converge. If the sequence converges, well, it seems kind of strange the way they write this. If the sequence converges, find its limit. It almost makes it sound like first decide if it converges, and if it does, then find the limit. Well, it's really the other way around. We first have to find the what?
The
The
limit.
limit.
And then if it's a single finite number, then we know the limit.
Whether-
You understand?
Yes.
Okay, so here we put 0. And we are good. Okay, any questions here?
No.
So let's try this one. And this one is the same idea as the rest of them, except that it has this factorial symbol, which also is, we're being asked to practice it up here with number 5. But notice it doesn't say anything about a sequence. It just says simplify. So to do number 11, we're going to have to simplify this first, just like they're asking on problem 5. But on problem 5, you stop after you simplified it, and you don't worry about the question about what's going on with the sequence. Just simplify. So I'm going to do this one with you, and then you could do the other one up there by yourself. So, and this was practiced as well in, well, I'm not sure, I can't remember, but you would have practiced in factorial expressions maybe before, but either way. So just a little recollection here that we would want is that, for example, whatever, 4 factorial, that's an exclamation mark in normal English setting, but in mathematics, it's factorial, and that the definition of a this has to be a positive integer. It can also be 0, but then that is a special definition of its own. And this is the one that doesn't make much sense at the moment, but it's a definition, so that doesn't mean it's necessarily provable, and this is not. So we have to just accept this, but this has a definition. Any other, all positive integers are the only thing you can have in front of a factorial, otherwise you would say it does not exist. So if you saw this, 3.1 factorial, you would say it does not exist because there is no value to that. There is no finite numerical answer to this. It's not infinity either, by the way, or any of the, it just does not exist. Anyway, what's the definition of 4 factorial or any positive integer factorial? There's 2 ways to write it. Authors tend to write it this way. You start with 1, multiply it times 2 times 3 and stop once you get to this number. So once you get there, that's when you stop. And then we could multiply it out if we wanted to, and that would be 24. And we could also write it though as, or since multiplication is commutative, we could also write it as 4 times 3 times 2 times 1, and that's the same thing. So either way. Okay. So what if I want to do one more numerical example before we do this one, and I hope that makes it easier for us to understand. So what if we had, for example, 4 factorial here, and we had 9, let's say 7 factorial here. And then the question is simplify. Well, a slower way to do it would be just to write it all out. And we would say, however you want to write it, 1 times 2 times 3 times 4, or 4 times 3 times 2 times 1. I just happen to like it this way. There's just because of what is coming over here. So that's just my preference. 4 times 3 times 2 times 1, and here 7 times 6 times 5 times 4 times 3, all the way down to 1. And then of course, this part, 4 times 3 times 2 times 1 has to be, the bottom number was bigger. 7 is a larger number than 4. So when you start to look at the larger factorial, you're going to end up, because that's larger, eventually you're going to get down to whatever this smaller one was. So this part right here, because it comes from the 7 and 7's larger, well, of course, if you started a bigger number than the one up here, by the way, these could be switched around. It wouldn't matter if 7's on top or 4's on the bottom. But because 7's a bigger number, 7 times 6 times 5, eventually you're going to get to whatever the smaller one is on the other piece, top or bottom. And so once you get to that, then these all divide out, because all of these divide out to 1s. So therefore, you have 1 left over. There's always an invisible multiplied 1, or you can just say these divide to 1. and you just have left the 7 times 6 times the 5. So what perhaps is a cleaner strategy is when you have something like this, you just do the following. You write the larger, so the larger factorial, you start to break it down. 7 times 6 times 5. When you get to the smaller number that's on the other piece of the fraction bar, in this case on the top, then, oh, I made it to 4, and that's what was up there is a 4. So instead of writing 4, 3, 2, 1, you can just write it as 4 factorial because that was what's up there anyway. And now this divides out to 1, and now you have the same thing, 7 times 6 times 5, and whatever that equals. You could multiply that out, and that would be 1 over 210 or something. You're like, well, that wasn't much difference of work. I'm just going to do it this way all the time. Well, that it's okay for this one, but if you had 80 factorial over 87 factorial, I don't think we want to write 1 or 80 times 79, blah, blah, blah. So here you'd want to take advantage of this strategy and the same, and then over here, we have no choice. You have to think of it like I'm showing you here. But on this one, you would say, which one's larger, of course? 80 factorial, 87, which one's larger?
87.
87.
Mm-hmm. And how about I make this an 83 just to, so I don't have to write so much. You could say 83 times 82 times 81. And then what would be next? We made it to what?
80 factorial.
80, yeah. And so instead of saying 80, 79, 78, all the way down to 1, just say factorial, because that's what's up here on the smaller part. Now that all divides out, and now you just have 1 divided by this stuff. Any questions here?
No.
And then you could multiply that on your calculator. You could whatever. Okay, so now this one. Because of these factorials, we need to simplify this first. Which one's bigger, class? N minus 3. Yeah? Which one is larger? Yeah? Would you rather have n cars or n minus 3 cars? What part's larger inside at least?
N.
N. So good. So the smaller factorial we keep. And this one we start to write its definition out, and we keep going until we get to the smaller one, and then we can divide them up. So, Joshua, what do you think? So this one's a little abstract here, but the first one's going to be what right here? So instead of saying 7 factorial, we start out with whatever this is, and we write 7, and then times the next one that's 1 less, the next one that's, so right here, this could have been written as 7. And this one could have been written, instead of 6, it could have been 7 minus 1. And then this could have been 7 minus 2. And that's another way to keep writing it, yeah? So what can we write here, Josh? We don't have any choice here because this is not a number, it's a variable. So what are we gonna have to, what does it start at?
N, and then n minus 1.
Mm-hmm. And then?
N minus 2.
And we keep going until we get to what is in the numerator or the other piece, yeah? And what would be the next, what's the next one?
N minus 3.
And the one after that would be n minus 4 and n minus 5 and n minus 6 all the way down to 1, which we really can't write them all down. So what should we do is say, oh, now I have the same as the other part in the opposing numerator and denominator, and now these divide out to 1. And now we have these three expressions left. N times n minus 1 times n minus 2. Any questions here, class, of just simplifying it? So this is just to simplify. That's simplifying. And now, well, so first of all, any questions there?
No.
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 Okay. And then what the heck were we trying to do in this problem anyway? We were trying to find out what do the terms, if we were to graph these dots or the terms of this sequence, does it converge to a single finite numerical value, or does it diverge to infinity only, negative infinity only, or alternating type? Yeah. So alternating, where it alternates not to a single finite number, I should say. So now we're going to take that limit. So now the limit, and there it is again, Denise. They didn't say anything about just infinity, did they?
No.
But I hope you know why we do that. Yeah. And that's why all that previous discussions of the graphs, I hope, pays off. Yeah. Okay. 1 over these three linear factors here. We could multiply all this out and get a single algebraic expression. There's really no need to, because let's see what happens when we take the limit. So in the numerator, it's a 1. There's no n here in the numerator to put an infinity in. So what happens right here, of course, Brian, we put what here for n?
Infinity?
And infinity minus 1 is still
Infinity?
Infinity minus 2 is still
Infinity?
And infinity times infinity times infinity, that just means a bigger number times a bigger number times a bigger and bigger number. It's like the same bigger and bigger number, but that'll just get bigger yet. So that's just what? On the bottom.
1 over infinity.
So yeah, technically not really supposed to write 1 over infinity, because that's not a number. But what happens when you have 1 divided by a larger and larger and larger number, which means it's going towards, so I could say like here towards infinity. But anyway, what does that answer become? So again, right now we're at the moment where we're going to get the determining value of this limit, which means the determining value of the sequence, the determining value of the graph of all the points of the sequence. Same way of saying, 3 ways of saying the same thing. And what's 1 divided by a larger and larger number, Brian? Of course, it's what?
It converges to 0.
Very good. And I like the fact that you said converges to 0, because that means you have a deeper perspective of what we're really trying to do here. So converges to 0. Great. So is that indeterminate, Brian? Determinate? What is that?
Determinate?
And which one of the 4 determinant is it?
Finite?
Finite, a single finite numerical value. Very good. And that means it converges. And it also means what? This limit what? Exists, does not exist, what?
It exists.
So all these different ways, and you can just see how it can trip people up. And I hope it's not. Any questions here, class?
No.
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 So we type 0 and check. And we are correct. So that's good. Okay. We need, well, maybe 2 or 3 more questions, but they start to go a little, oh, by the way, here's another one. All you have to do is simplify. Which one's bigger this time, n or n plus 2?
N plus 2.
So you start with the bigger one, and that's on the top this time. Remember, I was telling you it doesn't really matter where the bigger one is in terms of just simplifying it. So here all you do is simplify it and then you stop. You don't have to take a limit or anything. So we don't really have that much to go here, but I just don't know how long it'll take. But so this one is really quick. What's going to happen when you take, again, same thing here. So if you take the limit as n approaches infinity right here, what's 1 divided by a larger and larger number? Going to get closer to?
0.
0. And what's 5 to the 0 power? It equals what?
0.
5 to the 1 divided by a larger and larger number is 0. And what's 5 to the 0? Is that 0 or is that means
1.
1. So what is this limit then? So we just took the limit. I didn't write it down because I'm trying to go faster here. And so what kind of limit is this? Is this, it's not an indeterminate, it's a determinant. And what kind of determinant?
A finite numerical value.
Good. So that means this limit or the terms of this sequence, what? Converges, diverges, what?
Converges.
Converges to 1.
1.
You would just put a 1 right there. Yeah. And that one's pretty quick. This one is where the work we did in the last section or 2 pays off, because this was a peculiar one. I said it was going to pop up. So I wanted to go over this again, but we won't have to spend very long. The limit as n approaches infinity of, that's a really nasty looking infinity. Oh, well. And we have sine of n over n. So what happens when we put infinity in the denominator is just an n, so that's infinity. And it would be nice if this was an infinity, because you would have infinity over infinity, and we could use that's a friendly, that would be a friendly indeterminate if we can get infinity or negative infinity. But the sine graph is this oscillating graph that goes up to 1, down to -1, and so forth forever. And so when we're asked to take the limit as n approaches infinity of sine graph, well, this what? Does this get closer and closer to anything, or just keep on? No, this is oscillating instead of saying alternating, because it's a continuous graph here. Well, I guess it depends. Well, anyway, I guess I really was only supposed to write dots, because this is a sequence. But we do know the sine graph goes up and down forever, so it is a oscillating, alternating type. And is it getting closer and closer to any single finite number, or just keeps oscillating forever?
It just keeps oscillating.
So here we can write oscillating. We could write alternating, but it's a different kind of alternating. It's this, well, really it would just be some dots here, but whatever the dots are, they're going, they're going up and down forever. So it's an oscillating type. So this would be indeterminate. I'm sorry. this is, yeah, this is, when you get oscillating over infinity, it's an indeterminate, it's not determinate, because we can't even, how do I say this? I'm going to get my words mixed up to my mind here. So this is an indeterminate, but it's an oscillating indeterminate. And we don't know the determinant value yet. So it's an oscillating indeterminate. So it's not an unfriendly indeterminate. It's not a friendly indeterminate. We can't use L'Hopital's rule. And this was the strange one where we had to use the squeeze theorem, and it was like this. So we had to say, note or recall this mathematical fact that the sine graph, and technically I should write it as a function of x instead of with the ends. We know that it oscillates, like I showed you right here, from 1 to -1. And that's what this is a fact. This doesn't have to be proven. This is a mathematical fact that we know already from earlier coursework. And now we use this mathematical fact to try to figure out what this is. So this is missing the division of n, or the division of x. So now we take that previous fact above and we do something to it that will benefit us. That's mathematically, algebraically okay. And we divide everything by what is going to help us is if we can get x sine x over x. Instead of n's, we're writing x's. So we can divide an inequality statement by, if as long as x represents a positive number, then we can divide by a positive, something that represents a positive number, and that won't change the inequality signs. And we know that because n is going to infinity, so we're only looking at these positive values, or x are positive numbers. So then this is true. Because this is true, this is true. And now when we take the limit of this, we're gonna get the advantage of the squeeze theorem idea. And so we cannot take the limit of sine x over x, because when we tried, we got this up here. We got this oscillating between -1 and 1 idea divided by infinity, and that's an oscillating indeterminate. And it's a very strange, unique one that you get oscillating on the top and then infinity on the bottom. It could be reversed, by the way, as well. But that's even more rare. And so we now take the advantage of this fact divided by what we needed, so it looks like this. And now we can take the limit of this piece and this piece, and then we will get to use the squeeze theorem. So what happens, sine of x over x is getting squeezed in between this value and this value as you go out forever. So what is 1 over a larger and larger number? It's getting closer and closer to what?
0.
0. And the same thing on this side. -1 divided by a larger and larger and larger number. It's a smaller and smaller number, but it's just a -1. So it's like coming in closer and closer to 0, but from the negative side. So these are negative tiny numbers that are getting closer and closer to 0. Therefore, by the squeeze theorem, we know the graph of sine x over x as we go out forever and ever is getting squeezed by this graph above it, this graph below it. And because these two graphs, this one's below, this one's above, and both of these are getting closer and closer to 0. So since this one's always in between or touching, then this one is forced to also get closer and closer to 0. So we do know that sine of x over x is converging to 0 as well. And thus, if the function with the x's, which means the continuous graph here, if it converges to whatever this converges to, so does the sequence. Because the sequence is just not all of the graph, but just some of the dots on the graph. Oops, this is supposed to be an n, and now n converges to 0. Well, after you do this squeeze theorem 2 or 3 times, it starts to get a little tedious, and then you just kind of remember, oh, I have this sine x over x, and it's the same with cosine x over x or n over n. And you can also use the squeeze theorem, and then you just start to kind of remember that it converges to 0. So therefore, this does converge to 0. And 0. And check. And we have it. Yeah. If we looked at decimals here, well, I'm trying not to take so long. I'm trying to get it at maximum. I'm trying to find a compromise between different people's opinions on how extra time it should be. So I kind of come down to where at maximum, I'll go an extra to the absolute max to 130 and keep it at maximum 2 hours. So that's what I'm going to try to do. So some things then it kind of cuts, but not very much. So just a couple more here and we will be done. Okay. So of interest, the only thing different with these two here is we first have to figure out, oh, they don't even ask us to take the limit yet. Just recognize the pattern. They could have asked us to take the limit as well, but they didn't. So here, everyone, we just want to find the pattern. So this right here is when n equals 1, which would be a sub, oh gosh, it's hard to write. A sub 1, oh, let me write it over here. A sub 1 is when n equals 1, and that is a 6. And a sub 2, of course, is when n equals 2, and they give it to us, oh, but they give it to us as 5 plus 1/2. And so forth. And this is 5 plus, now you start to see a pattern, yeah? So 5 plus 1, 5 plus 1, 5 plus 1, 5 plus 1, but over 2, over 3, over 4, over 5. And so when n equals 3, you get 1 over the 3. When n is 2, you get 5 plus 1 over 2. We could go back and write this now as 5 plus, what do you guys think here? 1 over what instead?
N?
So you're right. That's going to be out here when we have the a sub n. So perfect. So the general idea will be, so this would be the nth term. Which is really the general formula, which this is the general, is the formula. Or the explicit formula which gives us all those terms. And you're right. The general formula is going to be 5 plus 1 over n. Okay, and this is going to be a sub n equals this term right here. So if we want to find any term on this sequence, we would use this. This is the rule or the formulaic expression that would give it to us. 5 plus 1 over n. But right here, I was just saying this first term, 6, would be 5 plus 1 over, what would be the n value you would put right here? Not a 2, not a 3, not a 4, and so forth, but just a what right here? What would be right here? When n equals what?
1.
And what's 1 over 1? 1 plus 5 is what?
6.
So that does give us the first term. Yeah. So the 6, we'd have to realize that could be broken down into 5 plus, just like the rest of them, but plus 1 over 1, and so forth. So I hope that makes sense. So then right over here, we're just going to put exactly that. So we're going to type 5 a sub n to get any term we want. You type, you compute, I should say 5 plus 1 over the n value. And that's what all these terms are. And then therefore the nth term represents any of these, all of these, by substituting a different n value. And that would be that. Now they could have asked us, hey, what's going on with these terms then as you go out forever? And that would be when we take the limit. So they could have asked us the second part, which is more interesting, is what's going on with this sequence as we go out forever. And it's pretty simple, pretty quick. Limit to make this limit into determinant value is very simple because direct substitution works. So of course, what's this going to be, class? 1 over a larger and larger number is going to be closer and closer to, what's this going to get closer and closer to?
0.
That's determinant. So when you add the 5, you get the complete determining value. And so that would mean all these terms are getting closer and closer to 5 as you go out forever and ever. And by the way, converging means it doesn't mean that you're going to necessarily ever get to 5, but you're getting closer and closer to 5. Okay?
Mm-hmm.
Okay. Any questions there?
No.
And this one, you're going to do the same thing. Find the pattern, but you don't have to take the limit. I just was just showing you. So you just write down the expression, whatever this pattern is. So I'll let you guys think about that. And so you can do those two. This one we already did. That was that 1 over infinity, which became 5 to the 0, which became a 1. And that was wherever it is. I lost it. Oh, up here. That's correct. Gosh, we did most of them. And I'll let you do this one. You can do this one, this one. So let's do one last one. Remember, this part means it's going to what right here, class? What's this -1 to the nth power mean it's going to do?
Alternate?
Alternate, good. And alternate like negativeness to positiveness, negative, positive, negative, like that.
Mm-hmm.
Now the question is it going to alternate without me doing the, is it going to alternate like this and just be the same number all the time? Like, doesn't have to be one and -1, but if it's alternating. Okay, sorry guys, my phone died. Can you hear me now?
Yes.
Yes.
Okay, thanks. I don't know how long you had that chat on. Hope it wasn't too long
No,
before I noticed it. Was it a long time or not too long?
no. I had
No,
just
no.
Oh, okay. Okay, so let's just finish this little idea and then we'll do this one and that's it. So this one I was trying to say to you all, this is an example of alternating between positive and negativeness, but are these terms are even, so when they're alternating, they could still alternate, but closer and closer to something. We did one earlier today where these terms started to, instead of what's happening here, they started to get closer and closer to zero. And though, even though they were alternating, they were converging towards a single finite number and it was zero. So you guys remember that?
Mm-hmm.
So when we have alternating, they can alternate but converge towards a single finite number, or they may not. So the first picture I was showing you right here, I guess these colors are not very different here, but they were just staying at 1 and -1, 1, -1, 1, and they're not getting any closer towards any single finite number. So in that case, they would be converging. I mean, they would be diverging, and because of the alternating type. So it would be determinant, but it would be the diverging determinant value. And it wouldn't be infinity only, it wouldn't be negative infinity only, it would be because it's alternating. And, or is it alternating but getting closer and closer to some single number? And that single number doesn't have to be 0, by the way. It could be another number. So it could be something like this, and I'm just making it up, but it could be like, here's -1. Oh, well, let me just, no, you don't need to know that part right now. So let me just go back to this thing. So this makes it alternating. Now the question is it alternating and staying, it not getting closer and closer to one finite number, or is it getting closer? So what we can do is take the limit, find out what's going on just with this part. Because this part makes it what right here, class? What does this part right here do? This makes it what right here?
Alternate.
Alternate. That makes it alternate from negative to positive. But is it this kind of alternating negative, or is it the type where it's getting closer and closer to one single number? And for it to be getting closer and closer to one single number, it has to be getting closer to 0 like that. So let's find out then, what is the limit of just this part? N over n plus 4. Whatever, if we get a number here, if it's 0, question mark. If we get 0, then what that means is, even though we know the numbers are alternating negative, positive, but they're getting closer and closer to 0. So that would be, again, like this type. Negative, positive, negative, but getting closer and closer to 0. And then that is that's an alternating type that's converging towards a single finite number. But if we're getting something like this, and let's say it goes like this: negative, positive, I'm running out of colors. Negative, positive, negative, positive, negative, positive. See here, it's alternating, and on one side it might be getting closer to some number, and on the other side it might be getting closer to some number, but on the negative side. So if that's the case, then this is getting closer to whatever this number is up here, and on the other side below, it's getting closer to whatever this number is underneath. But now, like half of it's getting closer to a positive number and the other half's getting closer to a negative number, and that's not converging to a single finite number, but converging. It's not really even converging, because it's to converge, it has to be to one finite number only. And this is getting closer to a number up here. Some of the points, half of the points are getting closer to a number above, and the other half of the points are getting closer to a number below. That's diverging. Does that part make sense?
Yes.
Yes.
So that's what we're going to find out right now. Is it this kind that's alternating but closer and closer to a single number? Or is it alternating where they're not getting closer to a single number? So let's find out. So if we just now look at this part only, we'll find out what's going on with just this part, and whatever we get, if we get 0, then the alternating part, it just means this one. Negative, positive, negative, positive, but they're all getting closer to 0 from above and below, so that would be converging. This would be an alternating converging to a single value, 0. And if we get anything else than 0, if we get 2, for example, if we get 2, if this part right here is 2 only when we take the limit, well, then that would be this kind. It's some of the points are getting closer to 2 and some of the points are getting closer to -2, and then that's diverging type. Or if you get a 3, if this limit turns out to be a 3, then the same idea, except this would be a 3 and this would be a -3, like that. I hope that makes sense. So let's find out. Do we get 0, or do we get 2, or do we get 3, or what do we get? So what happens when we take the limit right here? We get infinity over infinity. Infinity plus 4 is infinity, so we get infinity over infinity. So what's that called, of course, class? When you take a limit and you directly substitute and you get infinity over infinity, this is what?
Friendly determinant.
And that means we can use what rule?
L'Hopital's.
And when you use L'Hopital's, technically you're supposed to change the n's to x's. If you don't, it's not going to change the answer, but just want to point that out. And we could write derivative here with respect to x and so forth. And derivative with respect to x. And what do we get, of course? What's the derivative of x with respect to x? It's what?
1.
1 over the derivative of x, again, is what?
1.
1. The derivative of 4 by itself is?
0.
And so we get 1 over 1, which is 1. And now what happens, we've used L'Hopital's rule, and now we're ready to take the limit as n approach, you could say x, or n approaches infinity. There aren't any n's or x's here, or n's for that matter. So what's the limit? There's no place to put infinity in here, so we just get whatever this is, which is a 1. So that means this part only, the terms are getting closer to 1, but this part means it's alternating. So that means as you go out, the terms are going in one direction. Half of them are getting closer, not to -2 or -3, but half are getting closer to -1, and the other half is getting closer to 1. Does that part make sense right there, class?
Yes.
So then what do we say about this kind of limit then? So is this converging, or is it the alternating that's getting closer and closer to a single number? Or it's this not, is it? This is getting closer and closer to 2 different numbers. So is it converging or diverging?
Diverging.
So it's not this, it's this. So that means we're getting closer to +1 and -1, which means diverges. And then here we'll put diverges, yeah. And what kind of diverges? What, this is determinant. It diverges is determinant, but what kind? Is it infinity only, negative infinity only, or alternating?
Alternating.
And alternating towards one single finite number or towards more than one? Well, it doesn't have to be more than one. It's just, it's not it's not alternating, getting closer to a single finite number. I got to be careful trying not to use different words. So this is the determinant divergent type where it is alternating, but not closer and closer to a single finite number. Does that make sense?
Yes.
Okay, guys.
Yes.
Last one. I feel like I would be doing an in-service to you all if I didn't show you another way to find this limit. You're going to have to learn it sooner or later, and it's not very hard. When you get infinity over infinity like this, or 0 over 0, you can use algebra instead. And what we could have done right here, everyone, is take the n plus 4. It just takes like 30 seconds. And instead of, L'Hopital's was incredibly quick and incredibly simple, so perfectly fine. But there's going to be times when it's nicer to do what I'm about to show you, which is divide by, this is n to the first power. So the term in the denominator that has an n, there's only one of them here, and it's n to the first power. So that's the largest one. So what you can also do is divide by every term by n to the first power. And then simplify and take the limit there. So this is alternate to L'Hopital's rule. Excuse me. And you can only do it when it's polynomial, like on top it's polynomial, on the bottom it's polynomial. So we take the limit now, and as approaches infinity of the reduced form. And Brian, what's this going to reduce to when we simplify? This n divided by n is now just what?
1.
1. And on the bottom, n over n is just
1.
1. 4 divided by n does not reduce. So this is an alternate way to figure out this limit. You actually did this in Calculus 1. Just maybe depends how often. Maybe it was often, maybe it wasn't very often, but so it's easy to kind of forget. Now take the limit. And you cannot get a friendly indeterminate anymore because all you have left here is a 1. So that's not going to change. And what about here, Brian? 4, there's a 1 here. That doesn't change. Plus, what's 4 divided by a larger and larger number? It gets closer and closer to what?
To 0.
And now compute. And 1 divided by 1 is just 1. And that's what we did get by using L'Hopital's rule. We also got 1. And then you would have had to remember this makes it closer and closer. So this limit, wherever it was, is getting closer and closer to, well, it's not a single number. It's alternating between 1 and 1. I mean, it's getting closer to being -1 and 1. And therefore, it diverges. So it's the alternating type of diverges, that it's alternating but not getting closer and closer to a single finite number. So either way, this way or taking the derivative will give us the same answer. Any questions there?
No.
No.
So here we're going to put what here? This sequence does what? Does it converge towards a single finite number or diverge?
Diverge.
Diverge. And then we are learning more because we now are, I'm trying to get everyone to understand the different types of diverges. Otherwise, it's so easy to get lost, especially as we learn all the tests that are coming up after this section. So, yeah, so clear. And this one was diverges. And I didn't capitalize it, so we'll find out if it doesn't like that. It might mark it wrong, but it didn't. Okay, last one, number 9. So here is the sequence. And again, converge or divergence as we go out forever. So we want to look at the limit as n approaches infinity, right, Denise?
Mm-hmm.
Okay. And we can write this as what if we want? Instead of root radical form or root form, we can write it as n to the what power?
1/5.
Mm-hmm. And the same thing in the denominator. N to the 1/6 plus 4. Okay, so we take the limit, directly substitute, and going to a larger and larger number. And if we get a determinant value, well, then we're done already. Okay, if we get an indeterminate, well, then we have to do something to change the current form. So if we put infinity in, the 6th root, it's like the square root of infinity is still infinity. And so would be the 3rd root, or the cube root, or the 4th root, or the 5th root, or the 6th root. So the 6th root of infinity is still just what?
Infinity.
Mm-hmm. And the same in the denominator, the 6th root of infinity is still infinity, and infinity plus 4 is still infinity. So we get this friendly indeterminate. And that means we could use what, of course, Denise?
L'Hopital's.
So we can use L'Hopital's rule, good. Or we could divide these 3 terms by the highest exponent in the denominator, the highest exponent that's on the letter n. So if there was like a 3 here on the 4, that wouldn't count. It has to be the exponent on the letter, on the variable. So either way, we can get this. I don't know. Let me just show you this division one, and then you got, maybe we'll save. You could I'll let you try the derivative if you would want to. I mean, it's not very hard, either one. So you would take n to the 1/6, and you would take n to the 1/6. And again, the only reason I'm showing you this is because of future test, we're going to have to, it's going to require us to divide like this. So I just want us to kind of get used to it as well. So now divide by the highest exponent in the denominator on the variable of in the denominator, which is n to the 1/6. And this is very nice, especially with certain kinds of messy functions. So, okay. Well, before we take the limit as n approaches infinity, because before we got infinity over infinity, which was this friendly indeterminate. So what's one thing to do? Use L'Hopital's rule and see what happens. And then if we take it, the limit after taking the derivative, the top and the bottom independently, and we get a determinant value, we're done. Or divide by n to the 1/6, simplify it, and then take the limit. And if we get a determinant value, then we're also done. If we were to do this and get another indeterminate, well, then maybe we should have, you know, come up here and just use L'Hopital's. But it's hard to say. So every problem could be a little different. Well, anyway, but this quickly cleans up very nicely. So what's going to happen here, Joshua? End of the 1/6 divided by end of the 1/6 is going to divide out to what?
1.
Mhm. And as soon as you see that, that's good news because there's no way you can get infinity on the top anymore. That means we cannot get a friendly indeterminate. You might get an unfriendly indeterminate. That would be worse, but we're not. What's going to happen here then also, Josh?
You're going to get 1 plus 4 over n to the 1/6.
Yeah, and that's always going to happen where at least one of these terms won't simplify. But then we hope that when you take the limit as n approaches infinity, that this will become a determinable form. And what is now, when we take the limit, the 1 up here doesn't change because there's no n, where the limiting value, n getting bigger and bigger, doesn't have any impact up here because there's no n that will influence it. And the same thing here. But 4 divided by infinity to the 1/6 power, well, what's the 6th root of infinity again, Joshua? Of a bigger and bigger number, I should say.
Still infinity.
Mm-hmm. And what's 4 divided by a larger and larger number? It gets closer and closer to what?
0.
Mm-hmm. Oh, that just made it determinate right there. We got that part. So what's this going to become, of course, Josh? 1 over 1 is just what?
1.
1. And is this indeterminate or determinate?
Determinate.
And what kind of determinate?
Finite numerical value.
Good, which means what? The
It-
limit, I'm sorry?
It converges at 1.
Converges to 1, yeah. And that means, Joshua, that if we were to write these terms down or graph it, as you go out forever and ever and ever, you would never make it to 1, but you would get closer and closer to 1. Does that make sense?
Yes.
Okay. Oh, that's really sad. Converges towards 1. Okay. Which means this limit does exist. It has a finite numerical value, which is a way of saying it exists. And now here we just put 1. Any questions here, guys?
No.
So we type a 1 and we check. And we're good. Well, I think we did most of the homework, huh? Most of it. Let's see. So you have 2 there, and there's a 3rd, a 4th, a 5th. You might have like 6 problems left or something. Okay, these we didn't, I think we, anyway. So you have some problems left, but they should all be very manageable. And then on Wednesday, we start starting with section 9.2. And I'll change the due date. I was hoping to get on that as well today, but just takes a long time. But I hope all this made sense. And if it does, then the rest of the next 5 sections would give us a better chance for that to make sense. Okay, so okay, you guys also have a test to take if you haven't taken it yet. And I'm trying to remember if I had it due tonight or tomorrow night, or what night was it due?
Tomorrow night.
Tomorrow night. Okay, so you also have that to contend with if you haven't. I didn't check yet. I checked yesterday, but I haven't checked since last night if anyone's taken it yet. But nonetheless, that's due tomorrow night. So you can either finish this up and then worry about your test, or might want to just finish these up since they're fairly quick. Either way, we'll see you. Tomorrow there's Office online for 30 minutes if you need it. And that could be to go over any of these questions right here from 9.1, or if you have any questions from the previous sections in chapter 8 in which your test will cover. So you're also welcome to ask for that purpose as well. So any comments or general questions before we stop?
No.
sir.
No.
Okay. All right, guys, ladies, thank you so much for joining. I hope it pays off for you, and keep working hard, okay?
Thank you.
You're welcome.
Thank you. Bye-bye.
Bye.